All right, looking at the warm-up, number 1, we always ask ourselves when we see a problem, especially that involves a fraction, you ask yourself, can I simplify this? Can I reduce this? And no, you can't reduce 9/5. They're not divisible. There's no common factors there. So when that is the case, you take your radicand and you rewrite it as 2 separate ones. And then you play I Spy and you look for those perfect squares. You are going to be a pro at spotting perfect squares. The square root of 9 is a perfect square. It's plain old 3. So now we have 3 divided by square root 5. And we have that little checklist. There were 3 things on the checklist to know if we're really done solving a problem. Yep, and this one's disobeying that last thing. The denominator is irrational, and we need to force it to be rational, which means we need to rationalize the denominator. So we're going to rationalize the denominator by multiplying by a very specific number 1, a very intentional number 1. This is just the number 1. But I chose it because I'm trying to cancel out the radical in my denominator. So square root 5 came from the denominator. Multiply across the top, you get 3 root 5. Multiply across the bottom, square root 5 times square root 5 is 5. Final answer, 3 root 5 over 5. Good. The second one is easy enough to not even have to go to a separate screen. Take a look at those radicands. Square root 24, square root 6. 24 is divisible by 6. I'm allowed to divide them because they are both inside the radical. They are both radicands. So just divide these. 24 divided by 6 is just 4. So this problem is saying 3 times square root 4. Square root 4 is a perfect square. So it's saying 3 times 2. So the final answer to number 2 is a beautiful integer, 6. Very good. So you're always looking to see if those radicands are divisible, because if you had rationalized the denominator on number 2, you would have done a lot more work than everyone else. Number 3. We need a little bit more space for this. All right, put your algebra/pre-algebra brain back in and remind yourself, when were we allowed to add fractions? What had to be true for us mathematically, legally able to add fractions? Common denominator. Very good, Jane. They have to have a common denominator. Right now, those 2 fractions do not have a common denominator, so we need to force them to have a common denominator. But let's go ahead, and I think it's going to take care of itself. If we take this one right here, and we work with this one off to the side, I think it's going to take care of itself. When we rationalize the denominator, it's going to be 5. So let's go ahead and do that. I'm going to multiply the numerator and the denominator by square root 5. In the numerator, square root 2 times square root 5 is square root 10. Square root 5 times square root 5 is 5. So we're putting that back over there. So now we have 3 root 2 over 5 plus root 10 over 5. We're allowed to add those fractions because they have a common denominator. But now look at the numerator. Are we allowed to really simplify that numerator at all? 3 root 2 plus root 10. You have to remember to add radicals. They have to be the same radicand. You have to have a common like terms, in other words. They have to be like terms. They are not like terms. So unfortunately, our numerator is just that. And our denominator is, of course, 5. Because when you add 2 fractions together, you don't change the denominator. You keep that common denominator common. So the final answer to number 3 is 3 root 2 plus root 10 all over 5. That's the most simple the answer will get. Yep. All right, checking homework. If a triangle is a right triangle, then a squared plus b squared equals c squared. What is the converse of this statement? Do you remember converse? Remember, we have conditional, counterexample, converse, contrapositive. There are a lot of C words in logic, in geometry. But yeah, converse is kind of one of the most simple ones. You just reverse the sentence. If a triangle is right, then a squared plus b squared equals c squared. If a squared plus b squared equals c squared, then a triangle is a right triangle. So that's today's lesson, believe it or not, right here. We're zooming in on the converse of Pythagorean theorem. So go ahead and write that in your notes. I wrote it backwards on purpose. If c squared equals a squared plus b squared, then the triangle is a right triangle. So today in geometry is going to be backwards day. So might as well put on a backwards hat to remind you it's backwards day in geometry. All right, there we go, backwards. Write it down. So every time you write the Pythagorean theorem today, I want you to purposely write it backwards. C squared comes first, okay? All right, so let's try some. Oh, I skipped one. There we go. Example, is this triangle a right triangle? We love to assume, right? We love to look at that angle and we're like, oh, that's 90, boom, it's a right triangle. But we know we're not allowed to assume right angles. So, all right, so what did we agree to do? We agreed, excuse me, to write Pythagorean theorem backwards all day long. So, I'm going to take the largest side. Whichever side is the largest, that one is my C. So I'm going to take C squared, and then I'm going to take my A and my B. Oops. A squared plus B squared. So I'm arranging them like this, and I'm trying to determine are those quantities equal? So 50 squared, 2,500. 16 squared plus 48 squared, 2,560. Close, but not quite. Later in trig, we'll learn how to find out what that exact angle is. Well, one of the acute angles we can find out. But anyways, they don't equal each other. Therefore, this triangle was just a pretender. He is not a right triangle. Try another one. Triangle has lengths 13, 85, and 84. Is it a right triangle? So once again, we write it backwards. How do we know which one C is? It is always the longest one, the largest one. All right? So 85 squared, we write that first. 13 squared plus 84 squared. Did Miss Tanton Google Pythagorean triple? Is this a Pythagorean triple? Let's see. 85 squared, 7,225. 13 squared plus 84 squared. Look at that. 7,225. So, now we know how to tell, given three side lengths, whether they'll turn into a right triangle or not. We now know how to tell. All right? So if you had three pieces of wood and you knew their lengths and someone asked, could you build a right triangle out of these pieces of wood without cutting them, you would know if we could or not. Aaliyah, we are always assuming that the largest side is C and the two other sides are A and B. I'm not going to call them the legs because if it ends up not being a right triangle, then they won't be called legs. Okay, Aaliyah? So then this brings us to the all-important question. If a triangle is not a right triangle, then what is it? What are its choices? What are its choices in life? If it's not a right triangle, then it only has two options. It's either acute or it's obtuse. How do we know? How do we know? Let's go back to that one that was not a right triangle. We agreed this one wasn't right. It was wrong. But anyways, how do we know if this triangle, if the picture's not drawn to scale, how do we know if it is obtuse or acute? That's what we're learning about today. This is Pythagorean Converse. All right, let me show you using a fancy geometrical software called Geometry Sketchpad. You've already played with this during your assessment. All right, I have a triangle drawn. What do we know about that triangle right now? It is a blank triangle. Yeah, it's a right triangle. So we know it's a right triangle. And take a look. C squared, oh, I can't write on it, but C squared equals A squared plus B squared. 40, 40. Okay, now I'm going to manipulate this triangle and I'm going to turn it into a triangle that's not a right triangle. What kind of triangle did I turn it into? Look at the angle. An obtuse triangle. What do you notice about C squared versus A squared plus B squared? Is C squared larger? That's a greater than sign. or smaller? Yeah, they're not equal, but now we need to go deeper than that. Yeah, c squared's larger. Now, let me just keep playing with it. Maybe. Here we go. So my angle is getting bigger. C squared's still larger. It's kind of getting further away, isn't it? All right, let's go smaller. Is c squared still larger? Yeah. Let's go smaller. We're getting close. 97. Is c squared still larger? Yeah. Oh, 89. 89 degrees. Is c squared still larger? No. Now c squared is smaller. So I bet we can make a conclusion now. There we go. A triangle is acute if c squared is less than a squared plus b squared. A triangle is obtuse if c squared is greater than a squared plus b squared. And that is the summary of today's lesson. Sorry, skipping. There we go. Write it down. Equal to means it's right. Less than means acute. It's small. Greater than means obtuse. It's large. Do you see how important it is? It's so important that I'm wearing a backwards cap. Do you see how important it is that we write Pythagorean theorem backwards? If you don't write it backwards, then your acute one's going to be greater and your obtuse one's going to be less than, and that is confusing because acute goes with smaller and obtuse goes with greater. So please always play backwards day when you're determining whether a triangle is acute, obtuse, or right. Let's try some examples. So I'm giving you some lists of side lengths of triangles. And using our new Pythagorean Theorem Converse, we want to decide if it's acute, obtuse, or right. Do you recognize number 1? It is a Pythagorean triple. It is right. I'll give it away. But this is how we do it. You do c squared, and then you do a squared plus b squared, like we did on the first two. C squared, I'm going to go ahead and write the actual value, is 169. 12 squared plus 5 squared is 169. Since they're equal, the answer to the problem is right. Okay, next one. Which ones are C? All right. 15.8 squared, 249.64. 12.2 squared plus 10 squared. Oh, I made this one close, didn't I? Remember, the inequality is hungry. It's going to eat the bigger number. So I want to eat 249 because it's a little bit bigger than 248. That's a greater than sign. That means number 2 is an obtuse triangle. Number 3, c squared is 9. A squared plus b squared is 8. Oh, another obtuse triangle. 9 is greater. All right, last one, number 4. Uh-oh, which ones are C? Which one of those numbers is largest? Is it 2 root 3 or is it 5? Okay, it's definitely 5, yeah. All right, so 25. Now we have to do a squared plus b squared. Let's see. That's 4 times 3 plus 2. 12 plus 2. Not even close. So the answers were right. Obtuse, obtuse, obtuse. 3 obtuses in a row. All right.